Hello, everybody. This is a video going over the Unit 3 study sheet for Astronomy 151 that covers chapters 19, 20, chapter S2, and chapter S3. So let's start with the terms to understand. We have galactic disk, galactic bulge, halo, globular cluster. These are all elements of a spiral galaxy, of which our Milky Way is an example. The galactic disk is the part that contains the spiral arms. The galactic bulge is the center of the galaxy. The halo makes up what we call the spheroidal component, which is something that we'll touch on again a little bit later on. But you can imagine it as almost like a dome that fits over the disk so that it pokes way up perpendicular to our disk, moving up and then also downward. In other words, that means that we can really think about our galaxy as being almost spherical, where the galactic disk is just a portion that inhabits a very thin portion of our galaxy. Globular clusters are items that we touched on a little bit at the end of Unit 2. We know that they are clusters that are found in the halo of our galaxy, so they have stars that are on average older and redder than the type of star that you would find in the disk of our galaxy, or in other words, than the type that you would find in an open cluster. Dark matter is something that we touched on when we were talking about how the stars in the disk of our galaxy actually rotate the center of the galaxy. At first, if we wanted to just use what we learned about Kepler's third law back in Unit 1 to make a prediction as to how any object in the disk of the Milky Way should move around the center of the Milky Way, we would guess that Kepler's third law should still hold here. So in other words, that the further away you got from the center of the galaxy, we would predict that the orbital speed should decrease just as it does for the planets in our solar system. The fact that this is not what we observe is the best piece of evidence that we have for the existence of dark matter. The stars that are in the disk of the solar system, of the Milky Way's galaxy, all orbit at nearly the same speed. And if we think about how much additional mass is going to be enclosed inside of a circle, if we center it on the center of the galaxy, and if we imagine just pushing it outward by maybe even 1 inch at a time, for a spiral galaxy like our Milky Way, every inch we add to that is going to add a significant amount of galaxy inside. And if we imagine doing the same thing for our solar system, we would find that that's not the case. Once you move away from the sun, projecting a circle and then increasing its radius inch by inch is going to encompass a whole lot of empty space, so that the mass that any planet actually, the mass that is being orbited by any planet is going to be the sun plus a teeny tiny bit that's encompassed in that inch that you added to the radius. That is very, very different for a spiral galaxy like our own. Every inch is going to add a significant amount of mass. So this tells us that not all of the matter that we can actually see by shining light on it or by allowing light to travel from it to us, that can't possibly be the entire story. There's a second category of matter that is called dark matter that just doesn't interact with light in the same way as everything we've talked to up until this point does. The ionization nebula is something that you would find in the disk of a spiral galaxy. It's surrounding a forming or newborn star. So we know from our discussion in Unit 2 that a newborn star initially forms from a dusty gas cloud that starts to collapse inward. And the process that separates some of that dust from the surface of what's going to become the star is not a brief one. This lasts for a very, very long amount of time. So while a protostar is in the process of working its way toward getting onto the main sequence, it's still going to be swathed in dust for quite a bit of time. This allows for this protostar to heat up the nearby dust particles so that we can see or that we recognize it as an ionization nebula. But at the center of each one of those, we would find either a very, very young star or a forming star. Spin, as we are discussing it here with the spin-flip transition and then 21 centimeter radiation in particular, is something that we can link back to the concept of angular momentum, which we encountered for the first time in Unit 1. So when we were talking about one object whose whose size might be capable of changing, the angular momentum for that object was just going to be the object's mass times its rotation speed times its radius. And what that means is that any individual particle, like an electron or a proton, also has its own spin. So there's no requirement that the object actually change its size. If we know the size, if we know the mass, and we know the velocity, we can calculate the angular momentum for a particle. If we think about a hydrogen atom whose most common form is just one proton and just one electron, they have the same charge, they have different masses. The electron's mass is significantly less than a proton's mass, but their spins or their angular momenta have the option to either be lined up exactly the same, so maybe they're both spin up or spin down, or you might get one of each, one up, one down. And left to their own devices, those particles would prefer to seek out the lower energy version of that combination. And the lowest possible energy version of that combination would be one spin up, one spin down. So if we have a large quantity of hydrogen, some of it at any point in time is going to be oriented both up, some will be both down. But if we just wait, we can catch some of it going from either one of those states to the preferred state, one up, one down. That's what the spin-flip transition describes. The energy for two upward spins is equal to the energy for two downward spins, but they're both greater than the energy of one up, one down. The amount of energy that's released when either two ups or two downs evolve into one up, one down. That energy is very predictable. It's got a wavelength that correlates to a photon of 21 centimeters in wavelength. That means that anytime we see evidence of this 21 centimeter photon being released, what we're seeing is this spin-flip transition. If we specifically try to hone in on this 21 centimeter radiation, what we can do is take a picture of our galaxy from the interior that shows what the spiral arms look like. And that's incredibly powerful because we don't have the actual ability to send a camera outside of our galaxy and to take a picture of it. We're limited to seeing what our galaxy looks like from inside of it. But 21 centimeter radiation identifies the regions in between the spiral arms of our galaxy. The star-gas-star cycle is the term that is attributed to the very, very long-scale recycling process that a galaxy can carry out. We know from our discussion of star birth from Unit 2 that there has to exist some quantity of dusty gas that is not very, very high in temperature, but is relatively high in density. That's got to collapse in order for a protostar to start to form. And so long as it makes it through all four of those formation steps, it's going to end up as a real fusing star somewhere on the main sequence of the HR diagram. However, based on the mass of that star, we have a good way to predict exactly what should happen to that star at the end of its life. If it is below 8 solar masses, it's going to give rise to a white dwarf and a planetary nebula, but if it's above that, it's going to give rise to a neutron star and a supernova remnant. If we think about the supernova remnant and the planetary nebula in particular, both of those describe what used to be the atmosphere and the interior of the star when it was living. The core will turn into either our white dwarf or a neutron star, but everything aside from the core is going to be expelled outward so that it has the opportunity to spread out, to get dimmer, to cool down, and to contribute to those dusty gas clouds that are required in order for that very first step in star formation to take place. Bubbles and superbubbles just refer to different versions of the same idea. So a bubble might be centered on a star that is still living and then has an extremely high stellar wind. The superbubble is what you might end up with if you have a whole bunch of stars that are high mass and they die at around the same time. So this is a condition that is not really all that uncommon for open clusters, which are made up of a relatively small number of high mass, high temperature, high luminosity blue stars. If those all produce type 2 supernovae at around the same time, then their combined effect can cause a superbubble that has the ability to poke either up or down from the disk of the galaxy. And what that gives rise to is a galactic fountain, where material gets further away from the disk of the galaxy, it gets colder, and it's very similar to water in our own atmosphere. Getting colder means getting denser, it means getting less buoyant, and it means condensing into something that can then rain back down into the disk of the galaxy. A cosmic ray is created when matter that has mass is accelerated close to the speed of light. So we already know that any matter that has mass is never going to be capable of making it to the speed of light, but the type of matter that might be present when a star experiences a type 2 supernova means that it can get accelerated up to speeds that are near the speed of light, and the cosmic rays that result can be treated as not identical to, but similar to the photons that we talked about in Unit 1. We've got atomic hydrogen versus molecular hydrogen. We can tie this back to a concept from Chapter 5 when we were talking about how to get a material to change its phase. So if we started off with the solid version of any material and we just consistently added heat to it, we could get that material to start to melt. Then once it's completed the job of melting, we can continue adding heat to it. It'll start to, or to go up to its boiling point. And if we keep going, then it's going to be capable of boiling or vaporizing so that that liquid has been turned into a vapor. If we continue to keep going, we can create plasma, which is ultimately made out of just the nuclei of these materials so that the electrons are separate from them. But that requires a higher temperature than molecular hydrogen would. So, to say it another way, molecular hydrogen is the hydrogen that exists at a lower temperature because either the hydrogen that you started off with as gas hasn't been heated enough in order for all of its atoms to break apart. So for water vapor, for example, that would require that the H2O, so 2 hydrogens and 1 oxygen, would split apart. Atomic hydrogen is what you get if you keep going. So if we continue adding heat to this material, we can end up with ionized hydrogen, but increasing the heat or increasing the thermal energy is what takes you from molecular hydrogen to atomic to potentially ionized hydrogen. But the spin-flip transition that releases that 21 centimeter radiation is specific to atomic hydrogen. So that's going to happen at a slightly higher temperature than what's required for molecular hydrogen to exist. And molecular gas clouds are the first step of the star formation process. Next, we have metallicity, population 1 star, and population 2 star. These terms all go together because population 1 and 2 stars are not just distinguished by where you can find them in a spiral galaxy like our Milky Way, but the average masses of the stars you would expect to find in each population, and also the average age and temperature that you would expect to find in each population. So for population 1 stars, these exist in the disk of a spiral galaxy. So they're going to be stars of all ages because the disk of a spiral galaxy is where ongoing star formation takes place. Certainly, more stars that are small, red, and faint and cool are going to be generated for every star that is the opposite. So large, blue, luminous, and very hot. But because that's the only location where very large, very hot, very blue, very luminous stars can form, population 1 stars are going to be found in the disk of the galaxy. Population 2 stars are going to be found in the halo. So these are stars that you can find in globular clusters, like we mentioned beforehand. And because they're so far away from the actual location where star formation is capable of taking place, these stars on average are going to be a lot older, a lot redder, and as far as metallicity is concerned, they're going to have a smaller proportion of heavy elements. And as a reminder, heavy elements just refer to everything that is number 3 on the periodic table or greater. In other words, anything that's not hydrogen or helium. Population 1 stars are going to be a mixture of old and young stars, so the average metallicity is going to be a bit higher for that reason. The protogalactic cloud is the name that we give to the large structure that gave rise to our own Milky Way, and also the large structure that gave rise to each of the galaxies that exists in our universe today. The basic beats of the story are quite similar to what we saw when we were talking about star formation in Unit 2. You start off with a gas cloud that is able to hold equilibrium, but then loses that equilibrium somehow. And as a result, that loss of equilibrium is going to cause this protogalactic cloud to start collapsing inward. So, of course, this is going to be a much larger scale event for a galaxy as opposed to what produces an individual star, but the main beats of the story are very similar. The protogalactic cloud is not going to have the benefit of relying on the dust and the other heavy elements and molecules, like carbon monoxide in particular, that we discussed when we were talking about star formation. But a large, spread out, low rotation, relatively cold structure that collapses into something that's the opposite is the same story as what we saw when we were talking about star formation. The term cosmology just describes how the universe itself and everything contained in it evolves over time. So we're sort of shifting from paying attention to individual galaxies to thinking about how those galaxies move with respect to one another and how those galaxies, or I guess how those galaxies are embedded in space-time, which is something we'll say more about a little bit later on. Spheroidal component and disk component describe the two components that a spiral galaxy has. The spheroidal component is more like the halo and the material that you can find in the center of a spiral galaxy. The disk component is where you would find the spiral arms. For an elliptical galaxy, the spheroidal component is present, but the disk component and the spiral arms are not. For spiral galaxies, they can be categorized a handful of different ways. You have your ordinary spiral, where the galactic bulge is roughly round, or a barred spiral, where it is more of a rectangular shape. There's quite a bit of evidence that our Milky Way is a barred spiral, as opposed to being the ordinary type of spiral. Further on, we have the grand design spiral and the flocculent spiral, where this just describes how well separated the spiral arms of a galaxy are. So for a grand design spiral, it's very easy to see the spiral arms where stars of all colors and masses are located, and it's easy to see the gaps between those arms, where we would expect to find some of the dusty gas clouds that are going to give rise to later generations of stars. For flocculent galaxies, that is more difficult. We can perhaps tell where the disk is located by looking for dust lanes, because dust lanes only really exist in galaxies that have disks to them. But when you're trying to trace out one spiral arm compared to another one, it gets pretty difficult to do that with the flocculent spiral. Flocculent just comes from the Italian for the term fuzzy. It's not as distinct as the grand design spiral is. Galaxies can generally be categorized into spiral or elliptical categories. The lenticular galaxy is the type that has characteristics of each. So there might be a small amount of dust that's present in that galaxy, but nowhere near the amount that we would attribute to an ordinary spiral. But it also shows some characteristics that are pretty similar to the elliptical galaxy. The dwarf elliptical galaxy is just a subtype of the elliptical galaxy. This is the type of galaxy that is all a spheroidal component. It does not have a disk component. And as a consequence, it doesn't have the ability to replace stars as the original ones die out. So we're not likely to see much blue in this type of galaxy. We are likely to see lots of red, orange, and yellow. And of course, it's important to remember that stars that were born when that galaxy formed, some of them were blue. Not all of them were red and orange and yellow, but blue stars redden over time. So every galaxy is going to get redder over time as its original blue stars start to age. But the difference is that the elliptical galaxy doesn't have the ability to replace those aged blue stars with new blue stars. Elliptical and spiral are the two main categories, but of course there's no guarantee that every single galaxy will fit neatly into one of those categories. The irregular category is reserved for galaxies that do not fit neatly into either the spiral category or the elliptical category. Peculiar galaxies are distinct because they are the result of at least two galaxies interacting with one another. So that means that the way a peculiar galaxy looks now is not the way that either one of the individual galaxies looked when it was actually formed. When galaxies collide with one another, there is a wave of new star formation that's going to be triggered when just the material from one galaxy starts compacting and compressing into the material from the other one. And as a result, we can end up with some galaxies that look very, very peculiar or very unique compared to just our general spirals or ellipticals. Blue cloud and red sequence refer to sections that are on the HR diagram for galaxies. So when we categorize stars in Unit 2, we found that we could plot them on an HR diagram based on their surface temperatures, which is just another way of saying color, and their luminosities. That's just another way of saying absolute magnitude. Depending on where the star ended up on that HR diagram, we could determine whether it was still fusing hydrogen as the main source for its energy, or if it had aged off of the main sequence and begun shell fusion. We could also tell the difference between stars that were still living and fusing and ones that were not, like white dwarfs. There's not a diagram that works exactly the same way for galaxies, but if we plot luminosity on the y-axis and then color on the x-axis, we'll find that galaxies exist along a line that cuts from the bottom left-hand corner to the top right corner. We can call the bottom left-hand corner the blue cloud. The upper right-hand section is the red sequence. And since blue stars just get redder as they get older, we can say that any galaxy as it exists right now was bluer in its youth. So galaxies are going to start off on the blue or in the blue cloud, but as time goes on, they're going to age into the section that corresponds with the red sequence. Next up, we have galaxy group versus galaxy cluster. And group and cluster sound like they should be direct synonyms, but for this conversation, there's a distinction that's important for us to understand. The word group is used when we are referring to a relatively small number of galaxies that are collected together, but that group is dominated by spirals. The first time we encountered the term group was in Lab 10 when we were talking about the collection of galaxies that our Milky Way is a member of, and that collection is called the local group. It's dominated by the Milky Way and also the Andromeda Galaxy, which is another very large spiral, but that doesn't mean that groups are exclusively one type of galaxy. We can find evidence of ellipticals and irregulars that are fairly close to our galaxy, but we can distinguish between a group that is going to be dominated by spirals and a cluster, which is essentially the opposite. This is dominated by elliptical galaxies instead. Because of the way that elliptical galaxies group together, or collect together, is probably the best term to use there, we're liable to find greater numbers of elliptical galaxies collected in clusters, as opposed to the number that we would expect to find in galaxy groups. We have standard candle, which was a term that we first encountered when we were talking about distance measurements in Unit 2. The idea was that a standard candle was an object whose luminosity you knew independently of its distance, so that you could use it to calculate the distance just by comparing its apparent magnitude to its already known luminosity. And most of the objects we talked about in Unit 2 worked in the opposite way. We could make a judgment about their distance, compare that to some judgment that we made about their apparent magnitude, and we can use that to figure out what the absolute magnitude or what the luminosity was. Standard candles are unique because they allow us to get the luminosity first and to find the distance second. Look-back time is something that we encountered when we were starting to talk about the consequences of the expansion of our universe, and specifically the fact that light can only travel through a vacuum at a specific speed, which is 300,000 kilometers per second. So if light emanates from an object that is more than 300,000 kilometers away from us, when we receive it, it's going to be at least 1 second outdated. And the more distant that object is, the more outdated the light we receive from it will be. The light is going to carry an outdated image of whatever object it is that we're looking at, but the concept of look-back time is just meant to try to communicate the difference between what that object looks like right now and what it looked like in the image that we have right now. In other words, it's acknowledging that that object has aged and changed and evolved in the time that its light was taking to reach us. Cosmological redshift and cosmological horizon are also consequences of the expansion of our universe. Cosmological redshift is something that is fundamentally kind of similar to the Doppler shift that we talked about in Unit 1, but also a gravitational redshift that we talked about near the end of Unit 2. So just broadly, the Doppler shift is the name that's given to the phenomenon that describes how a wave is either compressed or expanded if it's being emitted from an object that is moving relative to the observer. So you can imagine waiting at a railroad crossing and hearing how the pitch of the train whistle seems to change as the train is passing you by. This is similar to what you would experience if you pull to the side of the road while an ambulance is passing you by and its siren seems like it changes. The idea is that if that object is moving towards you, you're going to experience a compressed version of that wave. And if it's a sound, you're going to perceive that as an increase in pitch. But once that object moves away from you, you're going to perceive the opposite. That wave is going to get stretched out so that its wavelength gets bigger, which means that its frequency gets smaller. So if it's a sound, you're going to interpret or perceive a lower pitch than what you heard when the object was moving toward you. And of course, if you are on the train or in the ambulance, you don't perceive that change in pitch because you're not moving relative to the source. Cosmological redshift is the consequence of the universe's expansion. So that is the type of motion that we're honing in on here. A galaxy moving away from our own is going to show an absorption spectrum that has familiar chemical fingerprints, but just ones that show up in a slightly wrong portion of the spectrum compared to where we'd expect to see them if it wasn't moving. So if we can recognize that chemical fingerprint, and if we can measure how different it is by the time we receive it, we can determine how redshifted that spectrum is. Cosmological horizon is just a consequence of the fact that light cannot travel at an infinite speed. So that means that all of the light that's been traveling toward us for the entirety of the existence of our universe can sort of fit inside of a cosmological horizon, something that we can imagine as almost being a shell that's centered on our galaxy and on our solar system. As time goes on, that shell gets slightly larger so that the surface gets slightly bigger. But that means that there are sections of our universe that are just outside of that horizon. So ones that are so far away that light has spent the entirety of the universe's existence working its way toward us and is still not there. Space-time is something that we touched on at the very end of Unit 2 for the first time when we were trying to make sense out of why black holes are possible and how they form. We imagined that if we could treat space-time as being like a rubber sheet, if you put mass on that rubber sheet, the sheet would curve, and the more massive the object was, the more curvature you would see. So that it was hypothetically possible that something could be so massive that if you are holding one of the corners of the rubber sheet, that object will cause it to curve so much that you won't be able to actually see the object that's responsible for the curvature. You'll just be able to see the curvature. Space-time is what you get when you take one temporal dimension, just assuming that time moves forward only, and you unite it with three spatial dimensions. You can think of up-down as one dimension, left-right as one dimension, and then back-forth as the last one. So space-time is four-dimensional, which means that that rubber sheet analogy is not a perfect one because we're thinking of that rubber sheet as being something that's two-dimensional. But it's a reasonable enough analogy that we can start to visualize how space-time curves in the presence of mass. Frame of reference is something that was very important when we were discussing special relativity or Einstein's special theory of relativity. We abbreviated that as STOR in some of our notes. And that attempted to describe how two observers who have different relative velocities would observe the same event. Frame of reference is just attached to your particular spaceship in that scenario. As a reminder, we were imagining that each one of us was in a spaceship. We could take a look at our lab partner, Al, who was moving in a certain direction at a velocity that was close to the speed of light. And what we would find is that if we asked Al to describe exactly the same situation, Al would feel that he was stationary and that we were moving in the opposite direction at the same percentage of the speed of light. So every single one of the velocities that we talked about way back in Unit 1 was really measured with respect to some frame of reference. And usually that frame of reference is going to be attached to Earth, or maybe attached to our solar system, or attached to our galaxy. World line and space-time diagram go together because a space-time diagram attempts to communicate how a person or maybe an object might move through time, and it balances that against how they move through space. So if you imagine that you are just moving in one dimension, so let's say only left to right, as time goes on, your position can be tracked so that you can build a graph that has a line on it. Not necessarily a line that has to have just one slope to it. That line is allowed to curve, but that line is referred to as a world line. We have gravitational time dilation and gravitational lensing. These are both related to the ideas that are described in the special theory of relativity. If we just take a moment to talk about the special theory of relativity, there were, in essence, 5 observations that we could make that describe how the special theory of relativity works. These are the 5 key ideas of special relativity. The first one is a familiar one. No material object can travel faster than light. No material object can travel as fast as light either, which is why we set up our thought experiments to assume that our scenarios all involved moving close to the speed of light. So 0.9 times c is something that we used a bunch of times. Next, if you observe something moving near light speed, it seems as if the rate of time flow will slow down for that object. It seems as if the length of that object will contract in the direction of motion, and it seems as if that object will behave as if its mass has increased. Not literally because you've added more atoms to it or more particles to make up that object, but simply just a consequence of motion very close to the speed of light. And then this last one, whether or not 2 events are simultaneous will depend on your frame of reference. So you as the observer in your reference frame might come to a different conclusion than your lab partner Al would, even though you are both observing exactly the same event. Okay, so time dilation describes the apparent change in time, the rate of time flow that you would perceive for your lab partner if they were near or if they were moving near the speed of light. So imagine that you are in your spaceship, you can see into their spaceship, and you can see a clock. It will always seem to you like the clock in your own spaceship is ticking at the appropriate rate, but that the other person's is ticking too slowly. Gravitational time dilation shows exactly the same result, but as a consequence of being in a gravitational field as opposed to moving close to the speed of light. What this means is that if we could compare a clock that was on the ground floor of a skyscraper to one that was at the top floor of the skyscraper, there would be an apparent disagreement in the rate at which time moves in those 2 reference frames. Gravitational lensing is the phenomenon that we can observe when light has to travel past something very massive before it can be received by us. Because it's traveling past something that's very massive, it's traveling through a heavily curved portion of space-time. However, that light is still trying to or is limited to moving through space-time in a straight line. It's just that the fabric of space itself is curved. Gravitational lensing sometimes allows us to misidentify or misperceive the actual position of an object based on where it appears like its light is coming from, compared to where it's actually positioned relative to that massive object. Gravitational waves are something we touched on at the end of Unit 2. We know that they can arise from events such as the collision of black holes or the collision of neutron stars, but what they cause is a ripple in space-time. So again, if we think about space-time as being sort of like the rubber sheet, if we stretch the rubber sheet out and let's say that you just take your finger and flick against the rubber sheet. The rubber sheet would start to vibrate, but those waves would propagate outward in a way that's not all that different from what we talked about in chapter 4, the first time we were discussing wave properties. These gravitational waves were things that were predicted by Einstein in his theory of relativity, but were only actually directly measured in the recent future. 2016 was the first conclusive measurement of gravitational waves. Wormholes in hyperspace are related to the curvature of space-time. If we imagine that the gray thing that we see here in our slide from our notes represents space-time, if space-time is curved severely enough, it should be possible for a wormhole or a tunnel to exist that links the upper part of this section of space-time to the lower part. So that means that you should be able to get from the upper part to the lower part in a shorter distance than what's required if you just moved along the surface of space-time itself. The proposed material that is in between the upper part of space-time and the lower part of space-time is called hyperspace. Wormholes have not been confirmed. They are hypothetically not actually ruled out. But again, there has not yet been any confirmation of this, so this exists just as a hypothetical concept at this point in time. Moving on to the equations to understand, we have the orbital velocity law that we used so that we could explain how much mass was enclosed inside of a circle of radius r that we could imagine projecting right on top of the center of the Milky Way galaxy. So this m sub r just references the fact that the bigger that circle is, the more mass will be enclosed inside of that circle. So if we wanted to try to calculate the total mass of our Milky Way galaxy, then this r would have to be as big as the radius of the disk of the Milky Way galaxy. If we considered a smaller r, that just means that we are only predicting how much how much mass is enclosed in the inner part of the disk of our Milky Way. R is just a subscript here on the left side, but on the right side here, that is the radius. V is the speed of a star around the center of the galaxy. And then capital G is the universal gravitation constant. We first encountered this in Unit 1. We weren't really concerned with its explicit value because it was a constant. It wasn't capable of changing. The same thing is true here, but if we change R, you would expect that we would change V at a normal, or not a normal, but a noticeable rate. And again, this is just highlighting the difference between how we can apply Kepler's third law to our solar system compared to how we can apply it to our galaxy. The orbital speed for stars in the disk of a galaxy is not significantly different for small r compared to large r. What that means is that if we rearrange this so that we can solve for an orbital speed, we have the square root of the universal gravitation constant, mr, the mass enclosed within some radius r, and then that radius r itself. So increasing that radius r has to increase the mass enclosed in that radius, and decreasing r would have to decrease the mass enclosed inside that radius. If we ignore capital G for a moment, mr over r is always going to be about the same value for the stars that are in the disk of our galaxy. Hubble's law is described here in equation form, where this velocity is equal to h0, which is the Hubble constant, times d, which is distance. This slide is from the Galaxies and the Foundations of Cosmology notes, and it shows a Hubble plot that has recessional velocity on the y-axis and then distance in millions of light years on the x-axis. This recessional velocity is one that we can determine by taking a spectrum of a distant galaxy and determining how redshifted it is. Because if it's redshifted, that's telling us that that galaxy is moving away from our own. The further you look into space, the faster these distant galaxies appear to be moving. So the slope of this line is h0, which is the Hubble constant. And in kilometers per second per million light years, this is approximately 22. But you can change the units that are on the x-axis of this graph. In lab, we tracked millions of parsecs instead of millions of light years. So our slope value was closer to 70 kilometers per second per million parsecs. The last equation in this list is one that we first encountered in Unit 1. It's the mass energy equation, where this is a subset of potential energy. This says that E is equal to mc squared, where c is the speed of light, m is mass, and then E is the energy content that's inherent in that mass. Concepts to understand. First, we can start with the star-gas-star cycle. So that is a description of how galaxies recycle the matter that is inside of them. If we start off with the formation of a generation of stars, we know we have to begin with a dusty gas cloud that's not too hot, but has a relatively high density, so gravitational collapse can begin and not be halted. As that gravitational collapse progresses, then our star is capable of making it through all 4 of the star formation steps that we discussed in our star birth discussion earlier on. If that star makes it onto the main sequence, then it's going to start fusing hydrogen into helium in its core, and depending on that star's mass, it will start to leave the main sequence and produce shell fusion, ultimately culminating in either a core that's filled with carbon for low-mass stars or a core that's filled with iron for high-mass stars. That star will either produce a planetary nebula or a Type II supernova remnant and leave behind either a white dwarf or a neutron star, potentially a black hole for the most massive high-mass stars. But the key idea is that that star is going to be incapable of returning 100% of its material back to the interstellar medium. Some of it will get locked up into white dwarfs for the low-mass stars. For neutron stars, for high-mass stars, that can get locked up into neutron stars. For the highest high-mass stars, this could get gobbled up by black holes. And we have to remember, not every object actually makes it all the way through the star formation process. So for the ones that start the process but just can't complete it, they end up as brown dwarfs. So items that never start fusing, so they can never produce a supernova remnant or a planetary nebula. So they have no way to return their material back to the interstellar medium. What this means is that the star-gas-star cycle does have a limit to it, because eventually, if enough of these cycles play out, a new generation of stars will not be able to form simply because the gas will not be dense enough in order for that first step of star formation to begin. The cosmological principle just describes the fact that expansion looks the same from all points in the universe. We can relate that to the balloon analogy that's described further down here. We can imagine the expansion of the universe as kind of being similar to the way that the skin of a balloon expands when you add air to it. If you put stickers on that balloon that represented the locations of galaxies, blowing up air wouldn't be capable of making the stickers stretch. But what it would be capable of doing is pulling the stickers away from each other. However, the stickers are always going to be stuck to the surface of the balloon, and galaxies are embedded in space-time in a sort of similar way. Allowing the universe to expand will pull galaxies away from each other, but what it doesn't do is allow galaxies to move through space away from one another. If we relate that back to the balloon analogy, that would be the same as the stickers actually sliding across the surface of the balloon. And that's not what we would observe in that scenario. That's also not what we observe when we examine our universe. If we imagined that we lived in any one galaxy that was in our universe, or any one sticker that was on the surface of the balloon, we would find that galaxies that start farther away from our own look like they're moving away from us faster. Ones that start closer to our own still look like they're moving away, but just not as quickly. Which galaxies do or do not have ongoing star formation? The general rule is that if a galaxy has a disk, then it has dust. If it has dust, it has the ability to replace stars as they die off. So galaxies with disks do have ongoing star formation. Ones that do not have them don't have ongoing star formation. The rubber sheet analogy is just one way that we can sort of visualize, at least partially, how space-time behaves when large masses act on it. The basic idea is that if you imagine a rubber sheet, if you stretch it out and then put a mass on that object, the larger the mass, the more it's going to cause that rubber sheet to curve, and a black hole is the result of a mass that's so large that you standing on the edge of the sheet can no longer actually see all the way down into the spout that large mass produces. The steady state model versus Hubble's law, that's just a reference to the fact that previous to conversations about the theory of relativity and then also Hubble's law, it was assumed that the universe was steady in the sense that it was always the same size, that size just being infinitely large, and that there was no difference between how the laws of physics worked at any particular location in space, and also no difference at any particular time in the history of space. Hubble's law tells us that our universe is not actually static in size, and as a consequence of that, if it is steadily increasing in size as time goes on, that means that in the distant past, it had to have been much smaller in size. The special theory of relativity is the one that we saw a few minutes ago. It assumes that the laws of nature are the same for everyone, and it also assumes that the speed of light is going to be the same for everyone. Notably, this hypothesis doesn't attempt to explain why this is true. It just posits that this is a reality of our universe, and it uses thought experiments and a few simple observations that we can make in our everyday life to prove that this is actually a characteristic of how our universe works. The 5 key ideas of the special theory of relativity are the absoluteness of the speed of light. So it is not possible for light to travel faster than 300,000 kilometers per second if it's moving through a vacuum. It's also not possible for any object with mass to reach 300,000 kilometers per second. We have the principle of simultaneity, which describes the apparent disagreement that two observers might have about whether or not two events are simultaneous. We have relativistic time dilation, which attributes the same observed results that we saw when we talked about gravitational time dilation to one object moving close to the speed of light where the observer is stationary. So it's the same result, but just caused by something different. Relativistic length contraction is described as the apparent shrinking in either the physical size of a spaceship, if from your perspective it is moving close to the speed of light. We can also take this to describe the apparent shrinking in the length of a trip. If we were imagining taking a very long trip many light years away, we saw an example in our notes about taking a trip to Vega, which is about 25 light years away. The disagreement between how, if we imagine twins here, the disagreement between how one twin would perceive the length of the trip in a spatial sense and how the other one would perceive the length of the trip in a temporal sense. These two ideas, fundamentally go together, time dilation and length contraction. And relativistic mass increase just describes the behavior of an object that's moving close to the speed of light. The closer you get to the speed of light, the more its behavior resembles an object that has an increased mass. The special theory of relativity is just like one portion of the general theory of relativity. These were separated by about a decade. The special theory of relativity was published in 1905, the general theory in 1915. And the general theory of relativity really kind of boils down to the equivalence principle, which tells us that the effects of acceleration can be perceived exactly the same as the effects of gravitation. We went through a handful of thought experiments imagining what you would perceive if you were in a room that was not moving at all, one that was moving up at a constant velocity, and then one that was moving up at a constant or with a changing velocity, so with a non-zero acceleration, in other words. And what we found was that if that room was accelerating up in exactly the right way, you would feel as if you had weight exactly the same way that you do when you're actually in Earth's gravitational field. So a reference frame that accelerates in exactly the right way can reproduce the effects of a stationary observer who is in a gravitational field. And then last here, we have the geometries of flat, spherical, and saddle-shaped spaces. Here's a slide from our notes from the S3 Spacetime and Gravity section of notes. If space is flat, then it has zero curvature. That means that we can approximate it as being the same as what you could draw on a sheet of paper. So the shortest distance between 2 points would be a straight line. Parallel lines would never get closer together or further apart as they propagate. If you draw a triangle, the interior angles are going to add up to exactly 180 degrees. And if you drew a circle, that circumference would be 2 pi times the radius of that circle. For spherical geometries, these rules change a little bit. The shortest distance between 2 points is a part of a great circle, so we can approximate that as being pretty similar to the way that we think of the equator on our own planet. Parallel lines eventually converge. It's the same way that we think about how lines of longitude behave on our planet. If you drew a triangle on the surface of a sphere, the sum of the angles would be bigger than 180 degrees. But if you drew a circle on the sphere, that circumference would be slightly less than 2 pi r. And then for the saddle-shaped geometry, each one of those rules now reverses. The shortest distance between 2 points is not just a straight line. It's also not part of a great circle. It is part of a hyperbola. Parallel lines will eventually diverge. So they'll get further and further away from each other the further they get from their source. If you draw a triangle on a saddle-shaped geometry, the sum of those interior angles would be slightly under 180 degrees. And if you drew a circle on a saddle-shaped geometry, its circumference would be slightly more than 2 pi r.